Somewhere in your body, right now, an electron has been moving for roughly 13.8 billion years. It hasn't stopped, it hasn't slowed down, it hasn't taken a single break since the first instant that atom formed, back when the universe was young enough to still be glowing. No fuel, no charging cable, no source of replenishment of any kind. And yet, physics says it will keep moving for as long as the atom exists, maybe forever. Say that out loud to a physicist and watch their face change, because on paper that shouldn't be possible. You've been told, probably since a middle school science class, that energy always runs out. Batteries die, fires burn to ash, stars, even stars, eventually go dark. So why doesn't the electron, why does this one specific, almost boringly small particle break a rule that governs literally everything else in the observable universe? Here's the part that should bother you more than it probably does. This isn't some fringe theory or an unresolved corner of physics nobody's gotten around to explaining. This is one of the oldest, most stubborn contradictions in the history of science. One that, for almost 2 decades, looked like it might tear classical physics apart at the seams. And the strange thing is, most people walk past it every single day without knowing it's there. You're made of these particles. Every atom in your hand, in your eyes reading this sentence, in the device you're holding, contains electrons that are, by every classical rule we know, supposed to lose energy and collapse. They don't. And by the end of this, you're going to understand exactly why, and it's going to force you to rethink what energy and motion actually mean at the smallest scales of reality. Let's start with the version of the atom you were probably taught, because it's the version that makes this whole thing so unsettling. Picture a tiny solar system. A nucleus sits in the middle like a sun, and electrons orbit it like planets, held in place by electric attraction instead of gravity. It's a clean picture. It's the one on the classroom poster. It's also, according to the physics of the early 20th century, completely impossible. Here's why. Go ahead and guess, if you had to bet, would you say a moving electric charge, spinning in a circle, radiates energy away or holds onto it? Most people's gut instinct is that it holds onto it, because nothing about going in circles sounds like it should cost you anything. But classical electromagnetism says the opposite, and it says it with total confidence. Any charged particle that accelerates, and moving in a circle counts as acceleration, because your direction is constantly changing even if your speed isn't, has to radiate energy in the form of light. This isn't a guess. It's one of the most well-tested equations in physics, derived over a century ago by James Clerk Maxwell and later refined by Joseph Larmor. A charge going around in a circle should continuously bleed energy into space as electromagnetic radiation, the same basic principle that makes radio antennas work. Now apply that to an electron orbiting a proton. If the electron is losing energy every instant, it can't stay in its orbit. It has to spiral inward, tighter and tighter, the same way a satellite with a decaying orbit eventually crashes into a planet. Physicists in the early 1900s actually did the math on this, and the number they got back was almost comically brutal. An electron orbiting a hydrogen nucleus, losing energy the way classical physics demanded, would spiral into the nucleus and the entire atom would collapse in about a 10/trillionth of a second. Not years, not days, a fraction of a second so small it's hard to even picture. Sit with that for a moment, because this is the misconception worth correcting right now. A lot of people assume the electrons orbiting like planets model is just a simplification, a slightly wrong but good enough way to explain something too complicated for a general audience. It's not that. It's not a simplified truth. It's a model that, if it were literally accurate, means every atom in the universe should have destroyed itself before your eyes could even register it existing. Every wall, every breath, every single thing you've ever touched is built from atoms that, according to the physics that works everywhere else, should not exist for longer than a blink that never even finishes blinking. And this wasn't some obscure calculation buried in a footnote somewhere. This was one of the central embarrassments of physics in the early 20th century, discussed openly, argued about in journals, treated as a genuine crisis. Historians of science sometimes call it the atomic stability problem, and for roughly a decade it sat there, unsolved, while chemists kept right on using atoms as if they were stable, because obviously they were. You could weigh them, react them, photograph their spectra with total precision. The atoms clearly weren't collapsing. Physics just couldn't explain why. Imagine being a physicist in 1911, watching an atom sit there calmly on a lab bench, doing exactly what your best equations say it categorically cannot do. That's not a minor inconsistency. That's the kind of contradiction that ends careers, forces textbooks to be rewritten, and eventually gives birth to an entirely new branch of physics. So here's the real mystery. It's not why don't electrons run out of energy? It's why hasn't the universe already collapsed? And for a brief, genuinely strange period in scientific history, nobody had an answer. This is where the story gets interesting, because the fix for this problem didn't come from someone patching a small error. It came from physicists realizing the entire framework, the orbiting planet model, the assumption that electrons behave like tiny, classical, point-like balls of charge, was wrong from the ground up. The first crack came from Niels Bohr in 1913. Bohr proposed something that, at the time, had no real justification behind it other than it works. He said electrons can only exist in specific, fixed energy levels around the nucleus, like rungs on a ladder. And as long as an electron stays on one of those rungs, it simply does not radiate energy. No explanation for why, no mechanism, just a rule bolted onto the model because the math finally matched what was observed in real atoms. You're allowed to be a little suspicious of that. Scientists at the time were too. It felt like cheating, like saying, the electron doesn't fall because I've declared, by decree, that it isn't allowed to. Bohr's model got the numbers right for hydrogen, which was a genuine breakthrough, but it didn't explain the actual reason electrons refused to spiral inward. It just assumed the answer and worked backward. The real explanation, the one that finally made sense of why an electron can move forever without losing energy, didn't arrive until physics abandoned the idea of the electron as a tiny orbiting ball altogether. That shift happened through the work of Louis de Broglie, Erwin Schrödinger, and Werner Heisenberg in the 1920s, and it's genuinely one of the strangest pivots in the history of science. De Broglie proposed something audacious in 1924. What if particles like electrons aren't just particles? What if they also behave like waves? Not metaphorically, literally. Every moving electron, he argued, has a wavelength associated with it, the same way light does. This sounds like the kind of thing that should have been laughed out of a physics department. Instead, within a few years, it was confirmed experimentally. Electrons fired at a crystal produced interference patterns, the unmistakable signature of wave behavior. The exact same pattern you'd see from ripples of water crossing through two gaps. A solid, physical particle behaving like a wave. Nobody in 1924 fully knew what to do with that. Schrödinger took de Broglie's idea and built an entire mathematical framework around it, an equation that describes the electron not as a dot moving along a path, but as a spread-out wave of probability surrounding the nucleus. And this is the piece that finally solves our puzzle. A wave doesn't have a single, definite location the way a ball does. It doesn't trace out a crisp, circular path you could draw with a compass. Instead, the electron in an atom exists as something closer to a standing wave. The same kind of pattern you'd get if you plucked a guitar string and watched it vibrate in a fixed shape rather than travel anywhere. A standing wave doesn't move from point A to point B. It doesn't accelerate in the way a planet does. And because classical radiation depends on a charge accelerating along a trajectory, a standing wave with no trajectory at all has nothing to radiate. Let that reframe sink in for a second, because this is the actual answer to the question in the title, and it's not what most people expect. The electron doesn't never run out of energy because it's somehow more efficient than everything else in the universe. It never runs out of energy because, at the smallest possible scale, the entire concept of an electron traveling along a path and therefore losing energy to that motion simply does not apply. You can't run out of gas on a road you were never driving on in the first place. It's worth pausing here, because this is usually the exact point where people either fall in love with quantum mechanics or quietly decide it's not for them. There's no shame in either reaction. This idea genuinely fights against how your brain evolved to interpret the world. Every intuition you have about motion, thrown rocks, orbiting planets, spinning tops slowing down, was built from watching objects large enough to obey classical rules. Nothing in your evolutionary history ever needed you to intuitively grasp a standing probability wave, so it's not a failure of intelligence that this feels strange. It would be stranger if it didn't. The physicists who first worked this out felt exactly the same disorientation, and some of them, including Schrödinger himself, spent years uneasy with the implications of the very equation that bears his name. But even this explanation, as elegant as it is, leaves a gap. And it's the gap that takes us to the real core of the mystery, the part almost nobody talks about outside of physics classrooms. Even in its lowest possible energy state, what physicists call the ground state, the electron in a hydrogen atom is never sitting still. It has energy, it has motion. And this is where most explanations quietly wave their hands and move on, because the honest answer is deeply weird, and weird doesn't always make for a clean textbook paragraph. Here's the misconception to correct directly, because I guarantee some part of your brain is still holding on to it. You'd think the ground state, the lowest energy an electron can have, should mean the electron just stops. Zero motion, zero energy, sitting quietly at the bottom of the well, like a ball finally coming to rest at the bottom of a bowl. That's what lowest energy state sounds like it should mean in literally every other context you've ever encountered the phrase. A pendulum at rest has zero kinetic energy. A ball at the bottom of a hill has zero motion. So why doesn't an electron do the same thing? The answer is a principle discovered by Werner Heisenberg in 1927, and it might be the single most quietly disruptive idea in the history of physics: the uncertainty principle. Heisenberg showed that you cannot simultaneously know both the exact position and the exact momentum of a particle with perfect precision. Not because our instruments aren't good enough, that's the part people usually get wrong. It's not a limitation of measurement technology that better microscopes will eventually solve. It's a fundamental property of reality itself. The more precisely you pin down where a particle is, the less precisely you can know how fast or in which direction it's moving. And the reverse is true too. Now apply that directly to our collapsing electron. If an electron truly stopped, zero energy, zero motion, sitting perfectly still at a perfectly known location right at the nucleus, you would know both its position and its momentum with complete certainty simultaneously. Position, exactly at the nucleus. Momentum, exactly zero. And the uncertainty principle says that combination is not allowed. It's not forbidden by some external rule-enforcing order. It is, in a very real sense, mathematically incoherent. Like asking what's north of the North Pole. The universe doesn't have an answer because the question breaks its own premises. So the electron is trapped in what physicists sometimes call an irreducible minimum of motion. It cannot come to rest because coming to rest would require violating the uncertainty principle. And the uncertainty principle isn't a rule the electron can bend given enough time or the right conditions. This residual, unavoidable, permanent energy, even at absolute zero temperature, even in the most stable possible configuration, is called zero-point energy. And it's not unique to electrons in atoms. It shows up throughout quantum mechanics, in vibrating molecules, in the vacuum of empty space itself. Even a vacuum, completely devoid of matter, has energy fluctuating within it, because nothingness isn't allowed to be perfectly, definitively nothing. That should sound insane. It is, by the standards of how we experience the world at human scale, completely insane. And it's also been confirmed experimentally, over and over, for the better part of a century. Think about what absolute zero means for a second, because most people picture it as the temperature where everything simply stops. No vibration, no motion, total stillness. That's actually the classical definition, the one physicists used before quantum mechanics rewrote the rulebook. Absolute zero, it turns out, isn't the temperature of stillness at all. It's the temperature where a system holds only the motion it is mathematically forbidden to lose. Helium is the cleanest real-world proof of this. Cool it down toward absolute zero, and instead of solidifying into a motionless block the way water does into ice, liquid helium keeps moving, keeps flowing, and under normal pressure refuses to freeze at all, no matter how cold you make it. Not because of some engineering limitation. Because the zero-point energy locked into the system is large enough, relative to the weak forces holding helium atoms together, that the atom simply cannot be pinned down enough to form a rigid, solid lattice. Cold, in this case, loses to uncertainty. There's an experimental confirmation of all this that's worth knowing about too, because it's easy to hear uncertainty principle and assume it's a purely theoretical construct, something mathematicians invented to paper over a gap in understanding. It isn't. The Casimir effect, first predicted in 1948 and confirmed in laboratory measurements decades later, shows two uncharged metal plates placed extremely close together in a vacuum, experiencing a measurable force pulling them toward each other. A force that only makes sense if empty space itself is seething with zero-point fluctuations, restricted between the plates in a way that creates a pressure imbalance. Scientists have measured this force directly, down to fractions of a nanometer of plate separation. That's not a thought experiment sitting comfortably inside a textbook. That's a number that came out of an actual instrument in an actual lab, matching a prediction built entirely on the same uncertainty principle, keeping your electrons from collapsing. Here's your reality check on this one, because it's worth being precise instead of dramatic about what's actually being claimed. The electron isn't magically immune to the laws of thermodynamics. It's not violating energy conservation, and it's not proof of some kind of perpetual motion machine, the way people sometimes excitedly and incorrectly frame it online. The total energy of the atom is fixed and accounted for. What's happening instead is that our classical intuition about what motion and energy and position even mean simply stops applying once you go small enough. The electron isn't cheating the system. The system at that scale runs on different rules than the ones your intuition was built for, the ones your brain developed watching balls roll down hills and pendulums swing to a stop. It's also worth being precise about what collapse would have actually looked like, because the phrase can sound abstract until you picture the mechanism. As the electron classically spirals inward under Lamar's equations, it wouldn't just quietly settle at the center. It would accelerate faster and faster as it got closer to the nucleus, radiating an increasing burst of energy in its final moments, essentially converting the entire atom into a flash of light before ceasing to exist as a stable structure at all. Multiply that by every atom in every object in the visible universe, all happening within roughly a 10 trillionth of a second of formation, and you're not looking at a slow fade. You're looking at a universe that, under classical rules, should have detonated itself into a wash of radiation in less time than it takes a single nerve impulse to travel 1 inch down your arm. That's the actual scale of the catastrophe quantum mechanics quietly prevented. This is where it's worth pausing on why this actually matters beyond being a fun fact for a dinner party. Because if electrons behaved the way classical physics originally predicted, spiraling into collapse in a 10 trillionth of a second, nothing you know would exist. Chemistry wouldn't exist, because stable atoms are the entire foundation chemistry is built on. Molecules wouldn't form, because molecular bonds depend on electrons occupying stable, non-collapsing orbitals around multiple nuclei at once. Stars wouldn't burn the way they do, planets wouldn't form the way they did, and, this is the part that should genuinely unsettle you, the specific arrangement of stable atoms that eventually became self-replicating chemistry, and then biology, and then you, could never have gotten off the ground. The uncertainty principle isn't a quirky footnote in a physics textbook. It's one of the load-bearing malls of the fact that a universe capable of producing anything as complicated as a person thinking about electrons is possible at all. And this connects to something worth sitting with for a second, because it reframes the entire question you came here with. You asked why an electron never runs out of energy, but flip it around. The electron isn't holding on to energy the way a battery holds a charge, doling it out slowly and eventually running dry. It's not spending anything. It never had a budget to run out of in the first place, because at that scale, existing and having energy aren't two separate things you can pull apart. The electron isn't fighting to keep its energy. It's simply doing the only thing quantum mechanics allows a bound particle to do: exist in a state where zero motion was never actually on the table. There's a deeper layer here too, one that connects this small-scale mystery to some of the largest structures in the universe. And it's the kind of connection that tends to get left out of shorter explanations. Zero-point energy doesn't just keep electrons from collapsing into nuclei. The same basic principle, that quantum systems can never be perfectly, definitively still, is a leading candidate in some models for contributing to the strange behavior of empty space on a cosmic scale, tied into ongoing research around vacuum energy, and, more speculatively, the search for explanations behind the accelerating expansion of the universe. Now, to be precise and not overreach here, this connection is still an active, unsettled area of research, not a locked-in answer, and you should be skeptical of anyone who presents it as fully solved. But the fact that the same underlying quantum principle, preventing your body's atoms from collapsing, might also whisper into questions about the fate of the entire cosmos, tells you something about how deep this rabbit hole actually goes. There's also a common follow-up question worth answering directly, because if you've made it this far, you've probably already started asking it. If electrons in their ground state never radiate energy, why does anything glow at all? Why do neon signs light up? Why does a flame have color? Why does a hydrogen lamp in a physics classroom produce that distinctive pink-violet light? The answer actually reinforces everything you just learned, rather than contradicting it. Light gets emitted only when an electron jumps between energy levels, when it absorbs energy from somewhere, a collision, an electrical current, a photon striking it, and briefly occupies a higher, less stable rung on that Bohr-style ladder. It doesn't stay there, it falls back down to a lower level, and in that transition releases the extra energy as a photon of very specific, predictable color. That's why every element produces its own unique fingerprint of spectral lines when you burn it or excite it electrically. Hydrogen's pink glow, sodium's yellow-orange streetlight color, neon's red-orange signature. None of that light comes from an electron losing its baseline energy the way a battery drains. It comes from an electron temporarily borrowing extra energy from an outside source and then giving that extra portion back, while its own irreducible ground state motion continues, untouched, underneath the whole process. The everyday glow of a neon sign, in other words, is a visible demonstration of exactly the mechanism this video just walked you through. Let's bring this back down to something you can actually picture, because all of this can start to feel abstract if it just stays in the realm of equations. Think about a guitar string again, because it's a genuinely useful comparison, not just a nice metaphor. When you plug it, it doesn't vibrate at just any random shape. It settles into a specific standing wave pattern determined by the length of the string and how it's fixed at both ends. The electron's wave function around a nucleus works on a related logic. It settles into specific stable patterns, the same energy levels Bohr first guessed at without fully understanding why they existed. But unlike a guitar string, which eventually loses energy to friction and air resistance and goes silent, the electron's wave has nowhere to lose energy to, because it isn't accelerating along a classical path in the first place. There's no friction against a path that doesn't exist. It's less like something running forever, and more like something that was never running down a track to begin with. Here's a question worth sitting with before you scroll away, because it's the kind of thing that separates people who just watched a video from people who actually understood it. If the uncertainty principle prevents an electron from ever having exactly zero motion and exactly zero position at once, does that mean, in some very technical sense, the electron in your body right now is, at this exact instant, in more than one place simultaneously? The honest answer is complicated, layered, genuinely debated in certain interpretations of quantum mechanics, and it's exactly the kind of question worth arguing about in the comments, because there isn't a single tidy consensus answer that ends the conversation. Take a guess before you look anything up. Are you in the camp that says the electron has a real, definite location we just can't measure? Or the camp that says the question itself doesn't have a definite answer until it's measured? Physicists have disagreed about this for 100 years. You're allowed to disagree too. It's also worth naming the historical irony sitting underneath all of this, because it says something about how science actually progresses, as opposed to how it gets portrayed in a lot of documentaries. Einstein, one of the towering figures behind the early quantum revolution, the same physicist whose work on the photoelectric effect helped kick off quantum theory in the first place, spent much of his later career deeply uncomfortable with where his own field ended up going. His famous line, that God does not play dice with the universe, was a direct objection to exactly the kind of fundamental uncertainty this video just described. Einstein wanted a universe where, in principle, if you knew everything, you could predict everything. Heisenberg and Bohr were telling him that no matter how much you knew, some things would remain genuinely, permanently undetermined until measured. Decades of debate between Einstein and Bohr on this exact question. Decades of some of the sharpest minds in physics arguing it out in letters and conferences, never fully resolved in either man's lifetime in a way that satisfied both of them. It's a useful reminder that even the people who built this science didn't always agree on what it meant, and being skeptical of a strange-sounding claim, even one backed by good evidence, puts you in good company. One more thing worth being honest about, because this channel doesn't do unresolved sensationalism for its own sake. None of what you just heard means physics has solved quantum mechanics in some final, complete sense. The uncertainty principle explains why the electron doesn't collapse. That part is on extremely firm experimental ground, tested to extraordinary precision for decades. But the deeper question of what's actually happening to a particle in between measurements, what a wave function really represents about physical reality versus what it represents about our knowledge of that reality, remains one of the most contested open questions in the philosophy of physics. This video gave you the mechanism. It didn't hand you a complete metaphysical picture of reality, because nobody currently has one to hand out. If any part of this made your brain do a small double take, that's genuinely the entire point of what this channel exists to do. Take the ideas hiding underneath ordinary things, the ones physics has actually solved, and pull them out into the light where you can look at them directly instead of just accepting the simplified poster version explanation. If you want more of that, subscribing means you don't miss the next one. And I'll be honest with you about why that matters to a channel like this. Every one of these takes real research time, chasing down the actual physics papers instead of recycling whatever's already floating around online. And that effort is genuinely sustained by people choosing to stick around for it. Because here's where this leaves us, and here's the thread we're picking up next. Electrons don't run out of energy because, at their scale, motion and existence are the same fact wearing two different names. But there's a related particle behavior that's arguably even stranger than everything you just heard. One where a particle doesn't just refuse to lose energy, it actually borrows energy it doesn't have, breaks straight through a barrier that should be physically impossible for it to cross, and gives that borrowed energy back so fast the universe never technically notices the debt. It's called quantum tunneling, and it's the reason the sun can shine at all. Because without it, the nuclear fusion reactions powering every star in the sky, including the one keeping you alive right now, shouldn't actually be able to start. That's next. And once you see how it works, you'll never look at sunlight the same way again.